welcome to Bare Metal Cyber, the podcast that bridges cybersecurity and education in a way that's engaging, informative, and practical. I'm Dr. Jason Edwards, a cybersecurity expert, educator, and author, bringing you insights, tips, and real-world stories from my widely read LinkedIn articles. Each week, we dive into pressing cybersecurity topics, explore real-world challenges, and break down actionable advice to help you navigate today's digital landscape. If you're enjoying this episode, visit baremetalcyber.com, where over 2 million people last year explored cybersecurity insights, resources, and expert content. You'll also find my books covering NIST, governance, risk, compliance, and other key cybersecurity topics. Cyber threats aren't slowing down, so let's get started with today's episode. Bulletproof the Cloud, building systems that survive outages and attacks. Cloud resilience is the foundation of modern digital infrastructure, ensuring that systems remain operational despite failures, cyber attacks, or unexpected disruptions. As businesses increasingly rely on cloud computing, designing architectures that can withstand outages and adapt to dynamic conditions is critical for maintaining availability, protecting data, and sustaining user trust. Achieving resilience requires a combination of fault tolerance, scalability, redundancy, and rapid recovery strategies, all while navigating the complexities of distributed environments, multi-crew dependencies, and evolving security threats. This chapter explores the principles of cloud resilience, strategies for architecting robust multi-cloud and hybrid cloud environments, techniques for mitigating failures and cyber threats, and emerging innovations shaping the future of resilient cloud computing, or principles of cloud resilience. Resilience in cloud computing is the ability of a system to maintain operational effectiveness despite failures, cyber threats, or unexpected disruptions. High availability ensures that cloud services remain accessible with minimal downtime, often achieved through load balancing, geographic distribution, and automated recovery mechanisms. Reducing downtime is critical, as even minor outages can result in financial loss, compliance violations, or damage to an organization's reputation. Protecting data and workloads goes beyond encryption and access controls. It involves designing architectures that prevent data loss during failures, ensuring continuity even if a critical service or provider becomes unavailable. Trust is a fragile commodity, and maintaining business continuity depends on proactive planning, redundancy, and rapid response to incidents that threaten service stability. A resilient cloud system is built on fault tolerance, meaning it can withstand hardware failures, software crashes, or even cyber attacks without causing major disruption. Scalability and elasticity allow cloud environments to handle sudden spikes in demand or reductions in resource use without compromising performance. This adaptability is vital in industries with unpredictable workloads, such as e-commerce during peak shopping seasons, or streaming services during major events. Redundancy and failover mechanisms ensure that if one data center, network path, or critical component fails, traffic seamlessly shifts to an alternative without users noticing. The speed of recovery from disruptions is another defining trait of resilience, as modern systems leverage automated healing, real-time monitoring, and disaster recovery strategies to restore normal operations in minutes rather than hours. Cloud resilience comes with its own set of challenges, particularly in managing the complexity of distributed systems. Unlike traditional data centers, cloud environments consist of interdependent components spread across multiple regions, often relying on different providers and technologies. The reliance on third-party services introduces risk, as an outage at a cloud provider, content delivery network, or authentication service can cascade into widespread downtime. Handling dynamic workloads means designing systems that can adapt to fluctuating demand while maintaining performance, a challenge compounded by the need for real-time monitoring and automated scaling. Managing cross-region dependencies adds another layer of difficulty, requiring careful planning to ensure that a failure in one geographical area does not bring down global operations. Organizations looking to strengthen their cloud resilience rely on established standards and frameworks that provide best practices for secure and reliable architectures. The NIST cybersecurity framework outlines key functions: identify, protect, detect, respond, and recover that help organizations build resilience against cyber threats. ISO 27001 sets a global benchmark for cloud security, ensuring organizations have a structured approach to risk management and data protection. Cloud providers also offer their own compliance guidelines, such as the AWS Well-Architected Framework, which helps businesses design resilient, high-performing, and secure cloud workloads. Industry best practices emphasize a layered approach to resilience, incorporating redundancy, automation, continuous monitoring, and proactive threat mitigation to keep cloud systems operational despite ever-evolving risks. Architecting for multi-cloud resilience. Adopting a multi-country strategy enables organizations to avoid vendor lock-in, ensuring they are not overly dependent on a single provider's ecosystem, pricing, or service availability. This flexibility allows businesses to choose the best services from multiple cloud providers, reducing the risk of disruptions caused by outages or policy changes. By distributing workloads across multiple cloud platforms, organizations can ensure that if one provider experiences an outage, critical applications can continue running on another. Disaster recovery capabilities are significantly enhanced in a multi-concrete approach, as data replication and failover mechanisms across providers create redundancy that mitigates the risk of catastrophic data loss. Leveraging provider-specific strengths, such as AI services from one vendor and storage solutions from another, enables organizations to optimize performance and cost while maintaining resilience. Multi-cloud load balancing is essential for directing traffic efficiently across different cloud providers and regions, ensuring high availability and performance. Global traffic management solutions use algorithms and real-time data to dynamically route requests to the best performing or least congested cloud region. Continuous real-time monitoring enables optimal routing by detecting latency, failures, or overload conditions and adjusting traffic distribution accordingly. Implementing provider-agnostic APIs helps organizations avoid integration challenges, allowing applications to interact seamlessly with multiple cloud environments without being tied to a specific vendor's infrastructure. Ensuring a consistent user experience across different cloud environments requires careful synchronization of application logic, security policies, and network configurations, preventing performance variations or accessibility issues. Cross-muter data replication is a critical component of multi-concrete resilience, ensuring that information remains accessible even if a provider experiences an outage. Replicating databases across multiple providers safeguards against localized failures while improving disaster recovery readiness. Ensuring data consistency in these distributed environments often requires adopting eventual consistency models, which allow systems to remain functional even when data synchronization is slightly delayed. Distributed storage solutions such as cloud object storage and database replication services help maintain durability and availability, reducing the risk of data loss. Synchronizing configurations and failover mechanisms in real time ensures that when a failure occurs, systems automatically switch to a backup provider with minimal disruption to operations. Integrating security across multiple cloud providers requires a unified identity and access management (IAM) strategy to enforce consistent authentication and authorization policies. Centralized IAM ensures that users and services have the appropriate permissions, reducing the risk of unauthorized access when managing multiple environments. End-to-end encryption of data in transit and at rest is essential for maintaining security across providers, ensuring that sensitive information remains protected regardless of where it is stored or processed. Consistent patching across environments prevents security gaps, requiring automation and policy enforcement to ensure all cloud resources remain up to date. Auditing and logging across multiple providers provide visibility into security events and system behavior, helping organizations detect anomalies, investigate incidents, and maintain compliance with regulatory requirements. Building resilience in hybrid cloud environments. Hybrid cloud environments blend on-premises infrastructure with cloud services, creating a flexible architecture that requires seamless integration to function effectively. Hybrid cloud gateways facilitate connectivity between these environments, enabling secure and efficient data exchange while maintaining control over sensitive workloads. Compatibility with legacy systems is a common challenge, as older applications may not be natively designed for cloud deployment, requiring refactoring or middleware solutions to bridge the gap. Secure and reliable communication channels are critical in hybrid environments, with encrypted tunnels, access controls, and authentication mechanisms, ensuring that data remains protected during transit. Monitoring workload performance across both cloud and on-prem environments helps organizations identify bottlenecks, optimize resource allocation, and proactively address performance issues before they impact operations. Dynamic workload orchestration enables organizations to manage computing resources efficiently across hybrid environments, ensuring workloads are placed where they are most effective. Containerization technologies such as Kubernetes allow applications to run consistently across cloud and on-premises environments, providing portability and scalability. Deploying workloads dynamically based on demand helps organizations optimize costs and performance, scaling resources up during peak usage and down during off-peak times. Automating failover between on-prem and cloud resources ensures uninterrupted operations, shifting workloads seamlessly in response to failures or maintenance events. Balancing workloads across environments for cost efficiency requires intelligent decision-making, as businesses must consider factors such as cloud pricing models, data egress costs, and on-prem capacity constraints when distributing computing tasks. A resilient hybrid cloud network relies on redundant connectivity to prevent single points of failure and maintain high availability. Establishing multiple network links, including fiber connections, leased lines, and cloud interconnects, ensures that data traffic can continue flowing even if one path fails. VPNs and direct connections provide secure, low-latency communication between on-premises and cloud environments, reducing the risks associated with transmitting sensitive data over the public internet. Latency mitigation is a key challenge in hybrid architectures, and edge computing helps by processing data closer to users or devices, reducing response times and bandwidth consumption. Software-defined wide-area network solutions enhance network resilience by dynamically optimizing traffic routing, prioritizing critical applications, and improving overall performance across hybrid infrastructures. Hybrid backup and disaster recovery strategies protect against data loss and downtime by ensuring that critical information remains accessible regardless of failures. Automated backup solutions continuously store copies of important data, reducing manual intervention and ensuring backups are up to date. Storing snapshots in both cloud and on-premises locations adds redundancy, preventing a single failure from compromising data integrity. Testing failover processes in secondary environments is crucial to confirming that backup systems function as expected, allowing organizations to refine their disaster recovery strategies proactively. Meeting recovery time objectives requires meticulous planning, as businesses must determine acceptable downtime limits and configure systems to restore operations within those parameters, ensuring continuity in the face of disruptions. Mitigating outages and attacks in distributed systems. Distributed systems, while highly scalable and efficient, introduce complexity that makes failure detection and isolation critical for resilience. Real-time monitoring with observability tools provides visibility into system health, performance metrics, and potential failures before they escalate. AI and machine learning models enhance anomaly detection by identifying deviations in behavior that could indicate impending failures or cyber threats. Implementing circuit breakers in microservices prevents a failing component from overloading the entire system by automatically stopping interactions with unhealthy services. Segmenting workloads ensures that failures in one part of the system do not cascade, allowing critical operations to continue running while affected components recover. Cyberattacks targeting distributed systems are a constant threat, making proactive defense strategies essential. Web application firewalls help protect applications from common threats such as SQL injection and cross-site scripting by filtering malicious requests before they reach critical services. Distributed denial of service (DDoS) protection involves traffic filtering and rate limiting to block large-scale attacks that can overwhelm infrastructure. Continuous penetration testing and red teaming simulate real-world attack scenarios, identifying vulnerabilities before malicious actors exploit them. Zero-trust architectures further enhance security by requiring strict identity verification at every access point, preventing unauthorized movement within a system even if an attacker gains entry. Fault tolerance in distributed environments ensures that failures do not compromise overall system stability. Redundant components and services allow operations to continue seamlessly when a primary system component fails, providing automatic failover capabilities. Database replication and clustering distribute data across multiple nodes, ensuring availability even if one database instance becomes unavailable. Idempotent operations and applications allow retry mechanisms to execute safely, ensuring that duplicate requests do not lead to unintended consequences or inconsistent data states. RAID configurations and erasure coding techniques improve data durability, protecting against hardware failures and reducing the risk of data corruption. Incident response and recovery mechanisms are crucial for minimizing downtime and ensuring quick restoration of services. Automating incident detection and alerting allows teams to respond to security breaches or system failures in real time, reducing the mean time to recovery. Predefined runbooks provide structured responses for various scenarios, enabling teams to act quickly and effectively when issues arise. Post-incident reviews analyze root causes and response effectiveness, helping organizations refine their strategies for future resilience. Lessons learned from incidents feed directly into continuous improvement efforts, ensuring that each failure strengthens the system rather than exposing recurring weaknesses. future trends and innovations in cloud resilience. Artificial intelligence is reshaping cloud resilience by enabling predictive and autonomous system management. Machine learning models analyze vast amounts of operational data to detect patterns that indicate potential failures, allowing proactive mitigation before disruptions occur. AI-driven capacity management dynamically adjusts computing resources in response to demand fluctuations, optimizing cost and performance without human intervention. Behavioral analytics enhance real-time threat detection by identifying anomalies that could indicate cyberattacks, insider threats, or system vulnerabilities. Adaptive scaling, powered by AI, ensures that cloud infrastructure can respond to unpredictable workloads, maintaining efficiency and availability even under unexpected traffic surges. Edge and fog computing are redefining resilience by decentralizing workloads, reducing dependency on centralized cloud infrastructure, and improving fault tolerance. Edge computing processes data closer to its source, whether in industrial sensors, autonomous vehicles, or mobile devices, ensuring that latency-sensitive applications remain functional even if the central cloud is inaccessible. This shift enhances performance for IoT systems, which rely on real-time data processing to support smart cities, healthcare monitoring, and automated manufacturing. Synchronizing edge and cloud data requires efficient replication strategies to maintain consistency between distributed nodes while preventing unnecessary data transfers. Security at the edge is critical as localized processing increases exposure to potential threats, necessitating encrypted storage, secure boot mechanisms, and hardened communication protocols. Cloud resilience is also being shaped by evolving regulatory standards, pushing organizations to align with global compliance requirements while maintaining system integrity. Regulatory changes impact how data is stored, accessed, and protected across cloud environments, requiring continuous updates to security policies and governance frameworks. International data protection laws, such as GDPR and CCPA, demand stricter data handling procedures, influencing how businesses approach cloud resilience on a global scale. Industry-specific resilience certifications are emerging to validate an organization's ability to withstand disruptions and recover swiftly. In multi-cloud setups, accountability becomes increasingly important, necessitating clear visibility into third-party dependencies, shared security responsibilities, and compliance reporting mechanisms. The looming threat of quantum computing is driving the development of quantum-resilient cloud architectures to secure data against future decryption capabilities. Organizations are preparing for post-quantum cryptography by researching encryption algorithms that can withstand attacks from quantum-powered adversaries. Ensuring future-proof encryption methods involves adopting cryptographic agility, designing systems capable of switching to stronger encryption protocols as quantum-resistant standards evolve. As quantum computing workloads gain traction, securing these environments requires new approaches to data protection, access controls, and cryptographic key management. Quantum-safe cloud solutions are in early stages of development, but enterprises that begin implementing quantum-ready security practices today will be better positioned for the next era of computing resilience. In conclusion, building resilience in cloud architectures is not a one-time effort, but an ongoing process of adapting to new threats, technologies, and operational demands. Organizations must integrate fault tolerance, redundancy, and intelligent automation to ensure high availability while balancing security and performance across multi-cloud and hybrid environments. As AI-driven monitoring, edge computing, and quantum-resistant security measures continue to evolve, businesses that proactively embrace these innovations will be better positioned to withstand outages and attacks. Cloud resilience is ultimately about preparation, leveraging the right frameworks, best practices, and emerging technologies to create systems that not only survive disruptions, but recover quickly and continue delivering value in an increasingly unpredictable digital landscape. Thanks for tuning into this episode of Bare Metal Cyber. If you enjoyed the podcast, be sure to subscribe and share it. You can find all my latest content, including newsletters, podcasts, articles, and books at baremetalcyber.com. Join the growing community and explore the insights that reached over 2 million people last year. Your support keeps this community thriving, and I truly appreciate every listen, follow, and share. Until next time, stay safe and remember that knowledge is power.